thank you for the introduction. So, today I will speak about TRAD test facility. So, the aim of this presentation is to give you a global overview of all the facility and equipment available at TRAD in order to perform tests. So, not only tests on electronic devices, but also tests on all material in the satellite. So this presentation will be divided in three main topics. The first one will concern the equipment for material testing. The second one will concern the facility for total ionizing dose testing. And the last one will speak about equipment and facility for single event effect testing. So let's start with the material laboratory. So you can see here a picture of the dedicated laboratory for testing material at TRAD. So as you can note on the picture, there is several equipment to perform tests on material. As you know, space is an harsh environment with several constraints, not only radiation constraints, but also UV radiations, vibrations, temperatures, vacuum, etc. And you have to test the whole satellites. You have to test the whole satellite versus this constraint. This is why we have developed a dedicated laboratory to do that. So the first equipment that I would like to speak is the solar simulators for UV irradiations. So this equipment allows to perform tests up to something like 15 cents. Of course, it allows to perform in situ monitoring, the UV flux and the sample temperatures. The only limitation now is that you have to test quite small samples because it's limited to 6 centimeters square, but with a good homogeneity of 10%. Of course, the UV irradiation was made in a vacuum. The chamber pressure is 10 to minus 5 millibars, and the equipment is in accordance with the norm. Well, all the tests made with this equipment will be in accordance with the norm. So this equipment is adapted to aging tests for materials that are directly exposed to space environment. The next equipment I would like to speak about is atmospheric thermal thickenings. So this equipment allows to perform tests in inert atmosphere, such as nitrogen, argon, or helium, with high temperature range from minus 170 to 400 degrees Celsius, with a rising and decreasing speed up to 20 degrees Celsius per minute. The chamber dimension is quite big. You can make tests on big sample. You can, of course, make in situ electrical measurements, and all the tests is in accordance with the norm. This equipment allows to assess thermal effects, and particularly at high temperatures. The next equipment is a special equipment specially designed by TRAD in order to perform vacuum thermal cyclings. So it is called cryovacs. So this equipment allows to perform thermal cycling with vacuum, of course. And the chamber pressure is around 10 to minus 5 millibar. And it allows to make this thermal cycling with high range temperature again, but this time with very low temperature because it is from minus 190 to 190 degrees Celsius. The rising and decreasing speed is up to 10 degrees Celsius per minute. The chamber dimension is limited to the plate because the sample is placed in the plate during the experiment. and the dimension of the plate is 20 centimeters per 11 centimeters. Again, we can perform in situ electrical measurements, and it is in accordance with a norm. These equipments allow to assess thermal effects under vacuum environments, especially at very low temperatures. The next equipment is an evolution of cryovacs. It is called tetavacs. So they have the same characteristics as the first one. The chamber pressure is better because it is 10 to minus 6 millibar, and the temperature range is minus 170 to 200 degrees Celsius. The rising and decreasing speed is the same as before. The dimension of the chamber is quite bigger because it is constituted by 2 plates this time. Each plate could be used separately to perform 2 tests, different tests in the same time, but can also be used both together in order to test bigger samples. Of course, we can make in situ electrical measurements, and you can perform tests in accordance with the norm. And this equipment allows to assess thermal effects in the vacuum environment. We also made an improvement on tetavacs with SWIPI. So SWIPI is a solar wind proton irradiator. It allows to simulate proton wind. The energy of this little accelerator is 300 eV to 5,000 eV. The chamber pressure is the same as before, of course, because it is tetavacs, in fact. The temperature range also, it's, of course, allowed to perform in situ electrical measurements. And it is adapted to hygiene tests for materials that are directly exposed to space environments. So the next big improvement of the material laboratory will be Vespa. So Vespa is the vacuum electron irradiation facility for SPAtialization. So it is a LINAC. It's allowed to use 4 different energy, from 1 to 4 MeV. The flux starts from 6 times 10 to the 7 electron centimeters square per second to 3 times 10 to 11 electron per centimeter square per second. The radiation area is quite big. We can make tests on big area, 30 square centimeters. And the vacuum is the same as before. You can perform irradiation in vacuum and or in inert atmosphere if you want. The temperature range is from minus 150 to 200 degrees Celsius. You can perform in situ electrical measurement, of course, and this equipment can assess to synergistic effects of temperature and radiation with in situ electrical measurements. Of course, we also have different equipment in order to test material. I will not show all the equipment today, but we also have equipment to perform optical measurements, transmissions, reflectivity and absorptivity, and electrical measurement, of course, voltage tests, voltage stress, insulation resistance, and of course, we also have optical microscope to perform observation and pictures of sample. So, now let me speak about the facility for total ionizing dose testing. So the facility is a bunker called Gamre. It is based on panoramic Cobalt 60 sources, so which is gamma irradiations, of course. The sources is from 14.8 terabecquerel to less in the few years, I think. The 2 main energy is the same for the cobalt, okay? The dose rate is from 10 rads per hour to 4 kilowatts per hour without any shielding. The facility is regulated in temperatures, of course, 20 degrees, and you can make irradiation with big sample because we have useful irradiation volume, 45 cube meters. So this facility allowed to assess to degradation induced by kilometer dose and samples, which could be electronic devices or material sample or everything you want. It is in accordance with the norm. So what you can see here in the picture here is the control room of the irradiation facility. In here it is the irradiation room. Let's focus on the irradiation room. So it's quite a big room, as you can see. The irradiator is here. This is the source holders. You can also see here the bias board structures. So this one is for high dose rate, what we can call high dose rate, and this one for low dose rate. So again, this facility allows to perform irradiation from 10 rad per hour to 4 kilorad per hour without any shielding. The next big improvement of this facility will be the bias board holder structure. We will replace it by circular one in order to improve the homogeneity and the space efficiency. And we also made a dedicated structure in order to perform low dose rate irradiations. So this picture was made with real experts. The simulations was done in order to be sure that the circular bias board holder structure will not affect the low dose rate structure. So we have speak about total ionizing dose, and now let's speak about the single event effect testing equipment. So the first thing you have to do in most cases in order to make a single event effect testing is to decapping component. You have to open component in order to be sure that the heavy ion will reach the die. So the first step is decapping component. So this is why we also have a decapping laboratory. It is dedicated to open components. You have different ways to open components with mechanical decapping and chemical decapping. So just before start any decapping procedure, you have to be sure to know where is the chip. This is why you also have an X-ray inspector. It allows to make visual inspection of the component, of course, to know where is the chip positioned, what is the package thickness, and it can help us to checking integrity and configuration of electronic devices before decapping operations. So according to the material of the package, we have to use dedicated machine in order to open it. So in order to open ceramic package, you have to use the milling machine. It allows us to thinning die for flip chip devices and to make us failure analysis. We can also use a cutting disc in order to cut devices. We can open component with it also, this one, but it is more dedicated for device cutting for cross-section analysis. And the wire saw is quite similar to the cutting disc, but with more precision. So, as you know, we test more and more CUTS components, and most of CUTS components is made of plastic package. In order to open easily plastic package, we also have chemical decapping, so it is based on acid attack. It is dedicated only on plastic package, and masks are used to define the size of opening in order to not remove all the package during the decapping procedures. So after the opening procedures, now we can make a test, single event effect test. So we have a dedicated laser laboratory in order to perform this test. So you can see on the picture here the control computer for the laser. The laser is inside the protected box, so you can see the optical head of the laser, and this is a bias board for testing, and here the test bench for the test. So this is a characteristic of the pulsed laser test. The laser is an Nd:YAG with wavelengths of 1064 nanometer, with a pulse duration of 790 picoseconds. It can be triggered from single shot to 50 kilohertz frequency pulse. The energy of the pulse is 0.06 to 135.9 nanojoule per pulse. The spot size can be chosen between 3, 1.8, 2.6, and 8 micrometers. So we can deplace the board with a 3 motorized linear stage, which allow to move the board with a resolution of 0.3 micrometers. We can also perform the test in front or back side of the die in order to scanning the deleted device. So this is an efficient tool for designers. It can help to improve the hardening process, but not only. We also use it as a debugging tool in order to prepare our tests in order to go to heavy ion facility. We also have another equipment in order to give us estimation of the sensitivity and also debugging our experimental setup. It is a californium test sources. So you can see it on the picture here. It is a vacuum chamber. So the ions that coming from the californium sources is around 40 MeV square centimeter per milligrams, and with a mean range of tens micrometers. So it allows us to perform the final test before going to heavy ion in vacuum, in real conditions, and this allows to give us an evaluation of the sensitivity and to validate definitively our test bench for single event effect testing. That's it. So the aim of this presentation was to give you a global overview of all the facility available at TRAD. I speak about facility equipment dedicated for material testing, facility dedicated for total ionizing dose testing, and also test means dedicated for single event effect testing. I thank you for your attention, and I remain at your disposal for any questions.